Okay, guys, so we're going to take a look at periodic variations of elements. It's important that we have covered electron configurations because this kind of takes advantage of that knowledge as we move forward. So the periodic table was developed by Dmitry Mendeleev in 1869. He was kind of also a year later, or within a year, Sir Lothar Meyer also had discovered some version of a periodic table. And so it was kind of providence because they both were not working on it separately. And yeah, so it's important to give him credit for it as well. It was arranged, the original periodic table is in order of atomic number, horizontal rows, which are going to be periods. I think I've said this in the past, but I'm going to formalize it now. They're known as periods, left to right. And then the vertical columns, known as groups, which we certainly know, had similar properties. So what he found was potassium, lithium, and sodium all reacted vigorously with water. They form the same oxides. Oxygen is super reactive. So generally you see what something will form in terms of an oxide or a hydroxide. And that is kind of the standard for determining what they how they chemically react. So reactive goes to water, chemical reaction, formation of oxides, chemical reaction, and then conductive, which is a physical property. So these things all matched up for potassium, sodium, and lithium. So he developed this idea of the law of octaves. So the law of octaves was kind of the original idea behind the periodic table. The law of octaves basically says that every eighth element, so here's my lithium, 1, 2, 3, 4, 5, 6, 7, 8. We have something that has similar properties. Then we go out again. And again, we have, so every eighth element, we're noticing there's something similar in properties. And what he has said at this point is, all right, well, every time we get something that has another element, we can start to place them based on the law of octaves. So even not being able to identify one, we're going to take a look at this highlighted one here and say, even if we have stuff in between, so here I have, they had discovered silicon, they had discovered tin, and they know based on positioning, based on atomic number, that there should be something in between the two. They called this ecosilicon, basically a substitute or just something they could put in the way. And what they basically stated was, all right, if silicon and tin have similar properties, the thing between them are going to have the average of silica and tin for those properties. So if we look at the density, we can take a look at the predicted properties of these things. So we can predict the properties of what ultimately germanium is going to have. So we can predict ecosilicon or germanium is going to have a similar density, similar density of oxide, similar melting point, similar oxide formation, similar boiling point of chloride. So of the chloride. So that is what they did. And you can actually see that there's some things that are right on, okay, and some things that are actually pretty close, all right? Same oxide as we would imagine, the same chloride formation, same or similar atomic mass that couldn't go out that far, but the average of those two is going to get. So it's giving rise it's giving rise to that there is a rhyme and reason to the periodic table. These things can be determined based on it. And so eventually they kind of developed this idea and noticed that similar properties. The left-hand side has metals, and I know that we've talked about this before, but metals are conductive. Nonmetals are insulators. Right, so they're noticing properties of all these different things. You know, metals are brittle, or I'm sorry, are malleable, where nonmetals are brittle. Metals are form positive charges, nonmetals form negative charges. And then, of course, semimetals are in between. They're not quite as lustrous, but they're not quite as matte as nonmetals would be. And again, we're starting to form some kind of rhyme or reason for our periodic table. And so there's a handful of discoveries or a handful of things that they kind of made when they finally got this all together. And first of all, again, I'm going to mention again, down our groups, across our periods, and we know that the principal quantum number goes down the side like that. So period 1, period 2, period 3. Again, this is period 6, period 7, the lanthanides and actinides. Okay. And they group these up. So this is the reason that I call this group 1 is because it is in fact group 1. And typically this is group 1A, Roman numeral 2A. This would be 3A, 4A, 5A, that's 4, 6A, 7A, and 8A. Down here, this would be 3B all the way up to was 3, 4, 5, 6, 7, 8, 9, 10. So it ultimately doesn't matter. They called those B's. Eventually, what we did is we just tossed that and said, it doesn't make sense to do that. Let's just call this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. The A block, A for the S and the P together, we call that the main group. Okay, so the main group of chemistry is kind of and the law of octaves works there. They did know about a bunch of metals, but they kind of clumped them in with other things until they got this form of the periodic table. I want to label just a few more things here. Group 1A, I'm sure I've said it before, is the alkali metals. Group 2A is the alkaline earth metals or alkali earth metals. Group 18, noble gases. Group 17, this is the most important one, is the halogens. You're going to hear that word used a bunch, so just know that that's the halogens. Group 16, this is never used, but I know it. Chalcogens. And group 7 or group 15 has a name, and they all have some special name. Okay. Yeah, so that's it. So they order the periodic table. We've got metals, we've got non-metals. Again, we have this little ladder that we need to know exists here. Okay, and so it's important that we know that this ladder does in fact exist. It shoots between a handful. Notice where the semi-metals are, which one the semi-metals actually are. Aluminum doesn't count, but anything else that's above or below that line totally does. Polonium we ignore because it's just non-existent. So a lot of these we just don't talk about, the 6 and 7, because they really don't exist much. So anyway, so this is what we got. All right. Good. So the periodic table, it's kind of come together. So now that we have a rhyme and reason, all of these properties are similar. There's a reason that the properties are similar, is because they're reacting similarly. So now what we can do is we can say, all right, well, let's understand the different properties and how we can actually make more sense of the periodic table. It's a magnificent discovery. So we're going to first talk about effective nuclear charge. And in fact, I might even stop it after this for the first video, because effective nuclear charge is kind of one of the most important things to understand. So please do your best to kind of take this and understand this. So watch this multiple times if you need to. So effective nuclear charge is the amount of positive charge experienced by an electron in an emitting electron atom. And we have to distinguish the difference, because generally when we're talking about electron physical, when we're talking about proton and electron interaction, we don't include other electrons, because the situation gets much more complex. So what is essentially happening is, and let's take a look at, let's say, a carbon atom. So I have a 6+ charge. And now I have electrons. I know we talked about the Bohr atom not really being a thing, but we're going to use it. I have electrons that are kind of around the outside. So this is my n equals 1, and this is my n equals 1 and n equals 2. Okay, so I have electrons that are around the outside. So I put one more. I can make this a little bit smaller. Next one. All right. So there we go. All right. So if this is my Bohr atom, I have electrons. 1, 2, 3, 4, 5, 6. And what we're interested in is we're interested in one of these outer electrons. Okay. In fact, let's take a look at this one over here. This outer electron. The Z effective portion of this, and this is the equation for Z effective. Z effective is, first of all, Z is not going to change. It is the atomic number or the nuclear charge. So in our example over here, my nuclear charge is 6. There are 6 protons in the nucleus. What we're really looking at is the Z effective portion of this, which is the effective nuclear charge, or what the effective nuclear charge is what an electron feels from the nucleus. Because we know that the electron is going to be held to the nucleus because it's positively charged and the electron is negatively charged. But the fact of the matter is, this right here being my Z effective, it is going to get blocked some by this electron. So that electron is going to get in the way and it's going to interfere with the interaction between that highlighted electron and the nucleus. So the effective nuclear charge is never the same as the actual atomic charge of the nucleus. And that is all looked at by the S, which is the shielding constant. Shielding of the valence electron. Okay, so we call it the shielding constant, the shielding of the electron. So if an electron interferes with that interaction, if the electron gets in the way of this interaction, it kind of cuts down on the effective nuclear charge. It cuts down on the interactions that field. So here's an example. If I have a light bulb, this light bulb has some certain intensity, so 100 watts, something like that. But if there's a globe on it, for some kind of frosted glass, all of the photons that are coming out are not actually what your eye observes. Your eye is going to observe a few of those photons because the frosted glass, the core electrons are blocking some of that light from getting to your eye. So it looks less intense. The nucleus is getting shielded by some of these electrons, and this interaction is less intense. Okay, so that's ultimately what effective nuclear charge is going to be. And so we can actually do these calculations to figure out what an effective nuclear charge is, and that's going to kind of drive the rest of our conversation. Okay, so that's the concept behind it. We're going to do a calculation for it in just a second, but that's the idea behind it. Not all S and P and all of their numbers are created equally. So 1s electrons are much closer to the nucleus. They screen the valence electrons. These things do a great job. Let's say we're talking about a 2p electron or a 2s electron. These are all in the way of, right? So because they are all congregating around this region, they're all in the way of that outer shell of electrons, that 2p electron. The 2p, on the other hand, the 2s electrons experience greater attraction than the 2p electrons. So we're actually seeing the same thing. They're shielding, but a good portion of the probability is actually outside of the 2s. So we run into the situation where the numbers are not exactly what they need to be. So ultimately, all of the different types of shells and subshells are going to behave a little bit differently. We don't have to get into penetration and all of that stuff, but we do have to recognize that the F, the D, the S, and the P are all very different based on where they are. Okay, and so with that said, I'm going to simplify it for you, and we're going to take a look at Slater's rules. So Slater's rules, again, let me put down the equation. Z effective is equal to Z minus S. So Slater's rules is going to be a method for us to determine S, or the shielding. Okay, so we're going to use Slater's rules to determine the shielding. So here are the rules for Slater's rules. So the S value, I use green because that's what I used above, is equal to 0.35 times any n electrons, or so I should say electrons with the same n value, okay? Plus 0.85 times electrons with n minus 1, plus 1 times electrons with n minus 2 or greater. So any inner electrons, okay? So these are Slater's rules. There is one small caveat that we have to take a look at, and I'm going to add that in. So for this one right here, electrons in F and D, so inner electrons, anything that's not in the outside shell, but in the inner shell, F and D electrons equal a full 1 shielding, because their penetration power is not as strong. They actually have actually it is strong. They have a very strong thing. So ultimately, what I'm going to do is I'm going to modify this equation. Instead, any electrons in n minus 1 that are S and P, and any electrons that are a full contribution times electrons with n minus 1, and these are going to be any electrons that are F and D. Okay, so that's the modified version of the equation. So anytime we run into an inner electron, not the outer end that's at F or D, we just basically have it's a full contribution. Okay, all right. So a couple of things. So this 2 plus down here too, by the way, this is after we get through n and n minus 1, this is all remaining electrons. We're going to do an example here, so it should hopefully make things just a little bit easier, or hopefully a little less complex. So let's start with that example, or let's do that example. So I want you to write the full electron configuration for bromine. Okay, so pause it here and do the full electron configuration for bromine. Hopefully what you got was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Okay, but of course I want to rearrange it so we have all the numbers in order, and that's just going to make our lives easier. I mean, we should get used to doing this anyway, because that's how we're supposed to do the valence electrons. So 3p6, 3d10, 4s2, 4p5. So there we go. So that's what we've got for the full. All right. So let's take a look at what we have. So first of all, I have my maximum n value is equal to 4. That means my n minus 1 equals 3. And then finally, my n minus 2 plus is equal to anything in the 2 and 1. So anything below 3. So let's do that. Let's highlight those. So n minus, so the n minus 2, maybe we'll start from the outside actually. Red. Here we go. There's my red. Anything in the n equals 1, or the n value, and that's going to be all of these electrons here. So any electrons that are actually there. Okay. Anything in the n minus 1 category are going to be all of the electrons that are in the 3. Okay. And then finally, any electrons that are in all of the remaining electrons count as n minus 2 plus. So one more time. So n minus 2 plus is going to equal a total of 8 electrons. Electrons in the n minus 1 equal 18. Count them all up. But again, the n minus 1, I have to divide into 2 categories. So we have 18 total electrons. but I actually have n-1 s and p electrons, which is 8 of them, right? So I'll just check all of these off that I've taken care of. And the f and the d electrons, I have, oh, sorry, let me put it in the wrong spot. So I've taken care of this and this. Those are my s and p n-1 electrons. Those are my n-2 plus electrons. I've got 8, I'm sorry, not 8, I actually have 10. Glad I did this, caught myself. 10 electrons there. And then I have 10 electrons in the F and D in the n-1, again, because we just have that special rule. And so a total of 18 electrons. And then finally, in my N group, I have a total of 5, 6, 7 electrons. 5, 6, 7. Good. Okay. So here's the rub before we actually do these calculations. Something to consider. A valence electron, or I should say it this way, the valence electron in question cannot screen itself. So we are doing this calculation to determine the screening constant of one of these outer electrons, right? So we're doing a screening for a 4p electron. But one of the electrons that I'm talking about is one of the electrons that I'm interested in. So I can't have an electron and have it screen itself. So we always have to do this. The number of electrons is not 6, or is not 7 electrons, it's actually 6 electrons. Because ultimately what we're doing is one of those 4p electrons is the one I'm interested in. So 6 electrons plus the 1 electron in question. Okay, so there's a couple of caveats to doing these calculations. After you do a couple, it's going to be easier. So again, one more time, I have 10 inner electrons. And again, I just look at one, just count all those up. I have 18 n-1 electrons, 8 from the S and the P, 10 from the D. And we don't have to do that calculation for anything else because they're always a full contribution elsewhere. Otherwise, I have 7 electrons in the outermost shell and the N equals N. But of course, one of those electrons I'm interested in, so actually 6 electrons that are causing screening because we're calculating a screening constant. So let's apply Slater's rules. The screening is equal to 0.35 times the 6 electrons plus 0.85 times 8 S and P electrons plus 1 times the 10 electrons, which are the D and the F. One for all the remaining electrons, which is 10 electrons remaining. And you do that calculation. When you do that calculation, you should end up with a Z effective, or I'm sorry, not a Z effective, that's important, a shielding constant of 28.9. So our shielding constant is 28.9. So now when we do this calculation, didn't realize I had all this other room over here. When we actually do this calculation, what is the Z effective of bromine, or what is the Z effective of the outer shell, the valence shell? And we always do we can do these for inner shells, but we always do this for the outer shell of electrons, the valence shell. So what is the Z effective? So Z effective equals Z minus S. Well, Z in this case is going to be its atomic number of 35. minus our shielding constant of 28.9. So the Z effective is equal to 6.1. What does that ultimately mean? What that ultimately means is the outer electrons of bromine feel a 6.1, like there are 6.1 protons that are pulling it inward. Okay. So if we think about this, what does this actually mean? What does this actually mean? So what we ultimately see is an increase in Z effective equals a stronger positive charge felt by outer electrons. So imagine what that means is if those valence electrons feel a very strong positive charge, okay, so the higher the Z effective, the more those electrons are going to be pulled in, right? So if I have a Z effective of 10, it's going to pull those electrons in tighter, right? So that's ultimately what we're seeing in terms of what Z effective actually tells us, okay? So again, increase in Z effectives means stronger charge felt by an outer electron. What that ultimately is that means that it's going to be pulled closer, pulled tighter to the nucleus, or tighter to that atom, which has a bunch of different effects. And we're actually going to see this in just a second, but imagine that. So it's pulled tighter to that nucleus. So if it's pulled tighter to the nucleus, that means it's closer. That means it is going to require more energy. To remove, right? So there are these effects that Z effective is going to help us drive. So down a group, I will just tell you the rules are essentially it remains constant down a group, okay? But across the period, we actually see an increase in Z effective. So the Z effective is not really a trend that we worry about much. What really kind of we look at is things like atomic radius. And I'm going to end it here and we'll start this again in the second video. But here I have, if I look along this row, what I see is, or actually I should say lithium, beryllium, boron over here, what we see is as we move from left to right, we're seeing a decrease in size, right? Because what's happening is Z effective is getting larger. Z effective means it's pulling those electrons closer and closer to the nucleus. Okay, so that's the importance of Z effective. All right. Okay, so we'll leave it here and I'm going to pick up next time, or next video is going to start here.